Hey guys, this is the lesson that we did. We compared some heights. We described our distribution, SOCV, with our context, right? We found some heights. We learned how to make an ogive graph, which I also call a cheater graph. And then we actually read one, and we used that to answer quarter 1, quarter 3, and IQR, and also to determine these values, okay? We did that in class, so you can get the notes from another student if you missed that. So in the next lesson, we started in class a review of z-score. So z-score is A minus P over S. You saw this formula back when you were in Algebra 2, let's hope. And I use this because it's easier to remember. So we always take our actual value minus our predicted value, which is our mean, and we put that over our standard deviation. And that tells us how far off we are. So we looked at Biff's score of a 65, and we saw if the mean was 80 and the standard deviation is 10, then this is 1 standard deviation below the mean, and that would be 2 standard deviations below the mean. So it makes sense that Biff is 1.5 below the mean. And that's actually what z-score means. Z is, if we took his actual score, 65, and subtracted it from the mean score of 80 and put that over the standard deviation that's 10, we end up getting negative 1.5. So it's very informative to Biff, because Biff can say, okay, I did worse than the average, and I did worse by an order of magnitude of about 1.5 of a typical amount that people varied. So the typical student varied by 10 to the left and 10 to the right. And notice Biff does have a score that's outside the typical outcome, okay? Outside even the typical variation of that. Now, what about Marty? Well, it looks like Marty, I'll use a different color, right? It looks like Marty was 88, and our pal Marty, always a Marty fan, right? He scored above the mean, and if 10 is 1 standard deviation, right, above, and these are below, so to signify above or below, we use this negative sign, right? We notice that he's a little less than 1 standard deviation above the mean. So his score, 88, his actual score, take away, we'd predict him to get the average, and we end up getting, that is his z-score. So it's not quite 1, and that number is exactly not quite 1. So that's what standard deviation means. Now digging a little deeper into our z-scores, right? I hope you try to attempt it. And again, we say this is actual. The actual value we're talking about, Biff or Marty or whomever, minus the predicted value over the standard deviation. This could also look like whatever actual value you're given minus your mean over the standard deviation. The thing here, though, is if I use actual and predicted over, then it spells AP statistics, and that's a little catchier, easier to remember. Okay, but the actual value and the predicted value is what would be the mean. If I don't know the person, I would assume they're an average person. Average height, average weight, average test score. Now, Goldie scored a 98 on the test. Find and interpret. So again, back in Algebra 1, you may have calculated this, but not really known what you were doing and why. So hopefully this class has given you an idea of why standard deviation is useful, and it's very telling. So let's first find it, and then we'll predict it. So the formula, if we plug in her actual value is 98, we'd predict her to get an 80, and the standard deviation is 10. So we get 1.8. And this makes sense. It looks like a 98 would be not quite 2 standard deviations above the mean, and that's exactly what we get. The number 1.8 is not quite 2 above. Now we must interpret. So what is the z-score? Well, we know that Goldie's scores, Goldie was the mayor, by the way. He was running for mayor. If these names ring a bell, they're from Back to the Future. All right, Goldie's chapter 1 test score is 1.8 standard deviations above, this is a plus sign, the mean. That's what it means when somebody says a z-score. It actually means something. Okay. So now let's look at a couple of operations and see if we can see a pattern here. Okay, it says there are 2 mathematical operations used when we calculate a z-score. So we're actually discovering what does a z-score and why does it work. So when we find a z-score, we take a minus p over s, right? So it says we first take each score and we subtract, right? The mean. Remember the mean was 80. So we took Marty's score and we subtracted the mean of 80, right? Fill in the table and then make a dot for each person. So what if we calculated, in a way, what we're doing here is we're calculating the top part of this, the score minus the mean, not just for Marty, right? And not just for Biff, but every student. So let's do that. It says fill in the table and make a dot for each. So make a dot plot for each score and then make a dot plot. So this is the dot plot here. It should kind of look like that. And this is the dot plot if we take the score minus the mean. So we have, what is that here? That'd be 62, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, this score is 61 would be a dot halfway in between, right? 65 would be in between 4 and 6. 65 again would be 4 and 6. 63 is between 2 and 4. 65 between 4 and 6. 67 between 6 and 8. Excuse me, 77. 78 is on the 8 here. On the 8 here. 79 between 78 and 80. We have an 80, a score of an 80, a score of an 80, a score of an 80. 81 is between 80 and 82. 88 has its own hash mark. 89 between 88 and 90. 93. 98 and 99. Looking at this dot plot, it should look a heck of a lot like this dot plot. It's just a little squishier. Now, we are supposed to subtract the mean from that. So in this box, I'm doing the score 61, take away 80. All right, so that would be negative 17, correct? 65, take away 80, negative 15, negative 15. 73, take away 80. Again, I'm just taking the score minus the mean. Negative 7, negative 5, negative 3, negative 2, negative 2, negative 1, 0, because 80 take away 80 is 0. Now, again, I'm doing the score of 88, take away 80, so I get positive numbers now. And then they're asking me to graph this here. Like, do you see how this they're asking me to graph that. So 17, so it would be 18, 16, 14, 12, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 2, 4, 6, 8, 12, 14, 16, 18. Okay, and these are negative, of course. So now let's do that. They asked me to graph negative 17, negative 15, negative 15, negative 7, negative 5, negative 3, negative 2, negative 2, negative 1, 0. 4 times in a row we got 0. Positive 1, positive 8, positive 9, positive 13, 18, and 19. Looky there, people. These dots look exactly like these dots. This is called transformation. All I did on a number line is move it from 60 to a 100 and shift it down to negative 17 to 19. But the range is the same. You know, the distance from the max to the min is exactly the same. The shape of the data is the same. Nothing is really changing here. So it says, write out what happened when we subtracted the mean from the data. The shape was the same. All right, looks like it's one mode, unimodal at 80. The peak is at 80. It looks relatively symmetrical. The center, well, hold on. The center before was at 80, and now the center is at 0. So the center is different. The center was 80 and now it's 0. So the center is 80 less than it was before. So in a way, in a number line, we moved it down the number line 80 points. Now, what about our variability? Now, we notice our measure of spread outedness, the dots spread outedness is exactly the same. We could also take our max minus min, 99, take away 61, we get 38. And the other number, we have 19, right? And negative 17. 19 minus negative 17 is, what do you know? I get a different number. So did I do the math wrong? Yeah, this is 61 take away 80 is 19. Okay, so if anybody was going crazy this whole time. Oh, and that makes sense. Yeah, because this dot is there. Yeah, negative 19. Sorry if you've been waiting for me to catch that mistake. If I make mistakes, I'll catch them eventually. Okay, so the max was 19. The min is negative 19, and that is 38. So notice the variability is the same. Second, when I did this formula AP statistics, right, I subtracted and then I divided by the standard deviation. So we want to look at what happens when we then divide by the standard deviation. What does that do to the shape, center, and variability of the data? So second, we take the score minus the mean, and we are going to divide. So I'm going to use a different color here just so we can see kind of this different step. Remember the standard deviation is 10, so we'll fill in the blank. After we subtract the mean, we are now going to divide by 10. So that's really handy. We'll just add a decimal place. And now we can make a dot plot. Okay. So negative 1.9, negative 1.5, negative 1.5, negative 7, negative 0.5, negative 0.3, negative 0.2, negative 0.2, negative 1, 0, 0, 0, 0, 0.1, 0.1, 0.8, 0.9, 0.3, 1.8, 1.9. I don't know about you guys, but this shape looks the same. This is not changing shape-wise. So shape, we stayed the same. Center, it was centered at 0. Now it's still centered at 0, so that stayed the same. So 0 divided by 10 is still 0. So when we look at the variability, we look at if it changed. So max minus min, here's our max, and there's our min. 1.9 minus a negative 1.9 is adding 1.9 to 1.9, which is 3.8. And that definitely changed, didn't it? It was 38, now it's 3.8. So our variability decreased, right? It's much narrower, and it was divided by 10, right? Our standard deviation. So to summarize, when we add or subtract the same value, 80, we subtracted 80 to every single value, we notice that in summary, our shape stayed the same. Our center, if we added or we subtracted 80, it went down 80. So if we added 80, everything would have gone up 80. So whatever value, so if we were to add or subtract the value of A, it would just add or subtract the value of A. And then the variability stayed the same. So again, just to kind of summarize what we said up here. When we multiplied or divided, which is we divided there, we noticed again our shape stayed the same. Our center looked like it didn't change, but it was divided by 10 and we just landed at the same number. So it was divided by 10. It just so happens when you divide 0 by 10, it doesn't change. So our center would have then gotten divided or multiplied by 10, whatever the value you're going to multiply or divide. So they would like us to call that B, so we'll call that B. And then last, our variability did change. Our variability was multiplied or divided. In our instance, it was divided by 10, so that would affect anytime we do that to any number by B. So lastly, what is the mean and standard deviation of the distribution of z-squares? Well, if we notice here, after we subtracted 80 from 80, we get 0. And we do that on purpose because we want to get to 0. And after we divide everything by 10, our standard deviation, so what happens to the mean after we do this subtracting and dividing? We end up getting the mean of 0. And what happens to our standard deviation? Our standard deviation of 10 ends up getting, so if we were off by 10, 10 minus 10 divided by, or what am I doing? Hold on. If we had a standard deviation of 10, so that would have been like you were 90 above the mean, 10 minus the mean of 80 divided by 10, that's what I meant by 10 by 10, would be 1. So all of our standard deviations have to end up being in terms of the standard deviation because the standard deviation minus the mean over the standard deviation would just give you 1, okay? This is called normalizing, and this is what happened back in Algebra 2. So we notice that our z value, our z would be whatever value we have minus our mean, and then we divide by the standard deviation. But in this instance, if we are the mean, we take the value of the mean minus the mean again, and divide by whatever the standard deviation is, notice that's going to give me 0 divided by the standard deviation, or 0. So that's why we get 0 if you are the mean. And this again is called standardized distributions, where we force the mean to be 0 and we force the standard deviation to be 1. So if you said, why is the mean always 0 and the standard deviation is always 1? It's like, nope, it's not. In fact, it almost never is. But we subtract the mean from itself and we divide by the standard deviation to force the mean to be 0 mathematically and force the standard deviation to be 1. And then we can do something with the data. Okay? So we finally got to our check for understanding. What does all this mean? Well, it means we can answer some questions about the data. And a lot of this is a review, like I said, from Algebra 2. So let's take a look. It says, according to the article of Yahoo News, you should change your sheets every 7 days at a minimum. To investigate sheet changing habits of adults, a random sample of 20, so we have 20 dots, are shown below. Suppose you converted the time before changing the sheets from days to weeks. Okay, so right now it's at days. What would happen if we changed it to weeks? So for instance, a value of 60 days would then be shown in the table. We have 7 days a week, right? In 1 week. So every single value in the table or in the data above would need to be divided by 7. So what did we learn in there so that we actually don't have to go through all the number? We can just learn from the result or the observation we made. We can say that and they want us to say about each of them, right? So we can say our shape won't change. We know the shape of our distribution in weeks is going to be the same as in days. The shape won't change when I convert it from weeks to days. And what is that shape? It looks like I'm skewed right. All right, what else? Well, our mean in weeks would be different, right? So our mean in days is 42.75 days. So if I converted this, I'd have to divide. And that when I divide the number 42.75 by 7, I get a different number, right? That would change it to the average would be 6.107 weeks. And that makes sense, right? Now, lastly, how would it change our standard deviation? So I ran out of room, so I'm going to go up here and change green. So how would my variability change? Notice our variability does change. If we divide by 12, then our variability would divide by 12. So our standard deviation in weeks would be the same as in days, 34,984 days, but we'd have to divide it by 7. So we'd get a standard deviation of 4.998 weeks. Now you're probably thinking, wait a minute, this is skewed data, so why are you using the mean and the standard deviation? You should be using IQR, and you're totally right. I'm using it though because they told me to talk about those values. All right, part B says, the adults in the study are given an article explaining the health benefits that would arise from changing their sheets more often. After reading the article, how does each person agrees to change their sheets 1 week sooner than they used to. Okay. So that's very interesting. What they're saying is if you change your sheet in 4 weeks, I guess a typical one changed it in 6 weeks, right? Every 6 weeks. then if everybody agreed to do it a week sooner, then everybody would be subtracting 1 week off of their current data. So a typical person, instead of doing it 6 weeks, would now do it in 5 weeks. How would that change our data? So again, here, all we were doing, we're dividing by 7. So that's going to divide the mean by 7 and divide the standard deviation by 7, right? So what happens when we subtract 1 from everything? Well, the shape should be the same, right? It's still skewed right. What should be the mean? Well, as I said, the average, if the average before was this and everyone agreed, then the average should be just 1 less than that. And what about the standard deviation? Well, we notice that from adding and subtracting, our standard deviation doesn't change. And you might, from adding and subtracting, make it, wait a minute, our standard deviation did change. But I have to remind you, no, it didn't. So let's go back. When all I did was subtract, notice my range didn't change. When all I did was subtract, look at my variability, it stayed the same. It was 38 and 38. So we know in this instance that if all I'm doing is subtracting 1, then it won't change. Okay, C, it says, now suppose you convert the time between changing seats from part B to a z-score. What would the shape, the mean, and the standard deviation be? So if I'm doing a z-score, all right, if I'm doing a z-score, then I'm both subtracting and I'm dividing. So that means the same type of outcome we saw before, the shape would stay the same. Skewed right. Right? Our mean would automatically go to 0 because we take the mean minus the mean and we divide by the standard deviation. So that would just be 0. The mean is always 0 when we use z-scores. And the standard deviation, what would happen? It looks like we'd take our standard deviation, divide by our standard deviation, and you'd always get 1, which is what we always get. And again, last thing, all standardized distributions have a mean of 0 and a standard deviation of 1. That's why we're able to use a standard deviation table. Thanks for joining me, guys. Check us next time.